Hello, I'm Matt Johnson, and welcome to my introduction on Coactive Design. Today, I want to challenge your assumptions and also give you a conceptual foundation for how to design and build effective human-machine systems. The title of this talk is No AI is an Island. It's a play on the classic poem that talks about no man is an island, and this claim proposes that as we pursue more advanced intelligent capabilities, it's advisable to remember that just as no man is an island, the same thing can be said about AI or robotics or any technology. A quick disclaimer, I'm going to use the terms robot, AI, and unmanned system and agent fairly interchangeably throughout this talk, as the need for teaming doesn't really change and the approach I'm about to talk about is the same in any case. My goals for today are twofold. First is to shake up your views on autonomy and AI. The second is to present an approach to understanding teaming based on interdependence. I'll start by discussing some of the myths of autonomous systems, and one myth in particular. We have a paper out there with some colleagues of mine called The 7 Deadly Myths, where we list out 7 different myths of autonomous systems, and we also have a supporting NASA webinar that extends that list. Today I'm really going to focus on one key myth, which is the role of AI. Very often the role of AI is seen as replacing the human. And I'd argue this is one of the most critical myths you need to try to avoid. This myth has been around for a while. It goes back to the days of Apollo and is captured very nicely in Dave Mindell's book, Digital Apollo. At that time, engineers who were building the system were thinking of this as a rocket that would take some carbon-based cargo off to the moon, and the people were just along for the ride. The astronauts, on the other hand, viewed the challenge as building a ship that they were going to pilot to the moon. These two views are characterized as black boxes versus gray matter, and the debate has been going on for a very long time. The real story with the Apollo program is how humans and automated technology work together to achieve this great accomplishment. Neither was likely to succeed alone. One other important takeaway is that people will continue to be a vital part of all but the least complex systems for the foreseeable future. The myth of replacement has taken many forms over the years. A more modern version that captures one of the key problems underlying this myth is the substitution myth. It's the idea that any new technology can be introduced as a simple substitution of machines for people, preserving the basic system while improving it on some output measure, like lower workload or fewer errors. In other words, you get all of the promised benefits and ignore any consequences or side effects. This brings us to the first lesson of the day. Autonomy is not replacement. Replacement is rarely what is actually happening with the addition of technology. Technology changes the nature of the work. Humans are often the enabling components of many technology systems, filling the gaps where technology fails. Most importantly, replacement is not the only or even the best way to view technology. In this cartoon depiction by Thomas Sheridan, you can see a human that's doing some work, represented by the box with an L inside. That could be a physical load or a cognitive load or some task work in general. The idea with replacements is that a computer, or AI, would replace that human being and carry the same load. This is a very simple way of using a computer. However, it's not the only way, and Sheridan pointed this out back in the 1970s. He listed a host of different ways that you could use the human and computer together. One way would be for the computer to be a backup for the human. The human and the machine could work together and supplement one another in parallel. Another possibility is that the computer can provide relief, allowing the human to carry the load easier. Another option, which we've added to Sheridan's original work, is that the computer could extend what the human is capable of achieving, allowing the human to lift the load higher, further, faster than it could on its own. These are all examples of different types of teamwork and explain how often when you apply technology to a human system, what you get is not replacement, but some interesting form of teamwork. Hopefully these different examples get you thinking about the different ways that human-machine teaming could be important. Technology does not work in isolation from people. As the title of this talk suggests, no AI is an island. For technology to achieve its full potential and deliver on its promised benefits, these systems will need to seamlessly work with and alongside people. Proper human and machine teaming is often the difference between a cool technology demonstration and something that is actually useful. So what is teaming? Human-machine teaming has been on their research agenda for many, many years now. If you look through some of the DoD calls, you'll see references to it all over the place. They speak about cooperative robotics, symbiotic relationships, human-system collaboration, combining the strengths, closely coupled systems, shared control, keeping the human in the loop or on the loop. But the big challenge with any of these descriptions of teaming is, what does it mean to an engineer? At the end of the day, most of these terms are fairly meaningless to an engineer. They're too vague and nondescript, and they don't map out to requirements, which is what the engineer actually needs to build this system. And so how do we get to a much more clear specification of what it means to team? Before we introduce the new approach, it's always good to look at the existing approaches to see what's missing. The earliest approaches are functional allocation and supervisory control. Functional allocation started in the 1950s with FITS characterizing the general strengths and weaknesses of humans and machines. In the 70s, Sheridan extended this work with the concept of supervisory control, where the human oversees autonomous systems, statically allocating tasks to them. For both of these, the foundation of the approach is task allocation. In the 80s and 90s, a host of new approaches were introduced: adjustable autonomy, sliding autonomy, adaptive automation, flexible autonomy. If you take an adjective that means change and put it in front of the word autonomy or automation, you have yourself a new approach. The commonality with all of these approaches is that they're really about dynamic task allocation, and the key insight is that static allocation up front at design time is not going to work. You're going to need to adjust things in real time, dynamically, in order for these systems to be effective. An important observation, but not sufficient to design for teaming. In 1999, James Allen introduced mixed initiative interaction. It's an interaction strategy where each agent contributes what it does best, and it shifted the focus from allocation of tasks to initiative and interaction. One problem with this is that the people who followed James Allen's mixed initiative interaction approach tended to follow more of a dynamic task allocation strategy, ignoring James Allen's insight into the importance of initiative and interaction. Summing up the problem with current practice, it tends to focus solely on autonomy or artificial intelligence, basically the capabilities to support task work. The main design question is what to automate, or worse, what can we automate? It's based on function allocation, which simplifies work, to task decomposition. The problem with this function allocation-based approach can be summed up by Peter Drucker. When it comes to the job itself, the problem is not to dissect it into parts or motions, but to put it back together into an integrated whole. This is the new task. He was speaking on the practice of management, but I would argue this applies also to human-machine system design. This brings us to lesson 2. It's not just about allocation, but also integration. At this point, I would like you to rethink what the goal of building an intelligent system really is. I'm going to use a simple example of an unmanned aerial system as the baseline. Manned aircraft have existed for a while, but they're very labor-intensive. They take an expert pilot to fly these things, and so the idea would be we could save money, effort, and improve safety if we can remove the man from the manned aircraft. The way we achieve this was to build a system that can fly independently, and we do that through what's called automation. Sometimes people refer to it as autonomy. Basically, the capability to fly the aircraft, maintaining altitude, heading, fly waypoints, etc. We've successfully achieved that, but that's not really the final goal of the system. The final goal of the system always ends up being a system that is interdependent, and the way you get at interdependence is not through more automation, it's through teamwork. This is why these unmanned systems today have a control station with one or more people at the controls. It's often argued that these people are there because the automation hasn't reached a sufficient level of maturity. However, this is a misconception. These drones today can take off, fly an entire mission, and return all on their own without human intervention. However, this still is not enough to accomplish the mission. Thus, we need the people behind the curtain. However, let's assume that you could replace these people. Would that get rid of the need for interdependence? I would argue the answer is still no, because even if this unmanned system was truly independent enough to operate without its controllers, it would still be interdependent within the Joint Air Operations Center, with other manned and unmanned aircraft, as well as with the soldier on the ground. We don't get rid of the interdependence, we merely change the boundaries on where it exists, which redefines what it means to support interdependence, but the interdependence will be there. This pattern of aiming for an independent system and then ending up needing an interdependent one is common in all technologies. You'll find it in sophisticated humanoid robots, advanced artificial intelligence, and even simple robots like the Roomba. This brings us to lesson 3. The goal should be building a system that can work interdependently. Consider the Roomba. Even though the task is simple, vacuuming, you don't eliminate the need for human-machine teaming. For example, you may not want that robot to come out while you're eating dinner or go into the baby's room. Another example is you may want to pause it and have it restart where it left off. While teaming is often ignored, particularly in the early stages of technology development, the need for teaming always arises as technology matures, and this was the case of the Roomba. There's an important implication in this, in that addressing that interdependence often requires complete redesign of the underlying algorithms, and that's why it's so important. For the Roomba, it was originally designed as a random bump-and-go algorithm. Very simple in its implementation, but very effective for vacuuming. The problem is, it's not very effective for interacting with people. If people want to set a time when it can come out, that means the job needs to get done. And if it's not done, they need to be able to pause it and restart it. Well, with the bump-and-go algorithm, you don't get that because you have no idea of where you've been or where you're going. And so Roomba had to redesign their algorithm to use modern SLAM technology to be able to track where it had been, realize when it gets paused, and then re-engage where it left off when it's restarted. That's just one example of how they had to change how they built the system as it interacted more and more with the human users. And Roomba's not the only one that went through this process. Most technology does. The Roomba example is pretty simple, but is interdependence really that important? I'll give you one more thought experiment. We'll consider a more complex team, like this group shown in this picture. Ask yourself, would these soldiers be as effective if they worked independently? I think it's obvious the answer should be no. Another question, if I replace one of them with a machine, could I do it without generating interdependence? Again, you'll find the answer to be no. And lastly, are these soldiers interdependent only at the surface, sort of a producer-consumer model, or are they deeply interdependent at the perception, understanding, planning, and execution? I think you're going to find they're deeply interdependent. And that really speaks to the importance of interdependence if you really want to get at complex teaming with technology. So lesson 4, there are important design implications when you start looking at systems that need to support interdependence. What it means is human-machine teaming is not a standalone capability. It is not that you replace your AI component with human-machine teaming. It's not a separate box that you add to the system after the fact. It permeates all of the design elements, the algorithms, and the interfaces. It should be viewed as an approach to what should be built and how to build it so as to imbue intelligent systems with teaming competence. The design challenge is how to identify and design support for interdependence. This is the purpose of coactive design. Coactive design is about designing human-robot systems that support interdependence. This is what separates the coactive design approach from other function allocation-based approaches. The fundamental principle of coactive design is that interdependence should be the thing that shapes the automation, not the other way around. This is counter to what you'll find in most system design today. So what does it mean to be interdependent? Often when people hear the word interdependence, they think dependence. Like when a train car needs a train engine to pull it forward, it depends on it. However, this is only one type of interdependence, a hard constraint. There are lots of other types of interdependence. Interdependence looks more like this. These two ladies are working together not because they have to, but because there's some benefit to it. They're willing to engage in some type of constraint on their behavior, the hand-holding, in order to get some perceived benefit from it, the value of extra stability. Interdependence is not about functions or tasks. Interdependence describes the set of complementary relationships that two or more parties rely on to manage required or opportunistic dependencies in joint activity. There's a couple key parts to this definition. First, it's not about function allocation or task work. Interdependence is about teamwork and relationships. Second, interdependence and teamwork is not just about hard constraints, but also soft constraints. Hard constraints are usually obvious to figure out because you can't get past them. Soft constraints are optional, and they're handled opportunistically. A hard constraint is a constraint that must be satisfied to be a feasible solution. On the other hand, a soft constraint can be violated, but violating the constraint incurs a penalty or misses out on some opportunity. These include things like progress appraisals, letting people know how things are going, or warnings, offers of assistance, and most backup behavior. None of these are required. All of them incur some cost, but they also provide some added value. Additionally, failure to support these soft constraints can have a cost as well. So what kind of relationships are used to manage dependencies in joint activity? If you go to the internet and look up human-machine system design, you'll find all kinds of models, and they look very different. They'll talk about things like commands and signals, interface and autonomy, and a whole host of other terms. But at the end of the day, all of these diagrams can be boiled down to one simple diagram of a human connected to a machine by a double-headed arrow. This is Thomas Sheridan's original diagram, which shows a human connected to a machine by a double-headed arrow. The right-hand side is where automation and control theory people live, and they build the algorithms and components that drive that machinery. The left-hand side is where interface designers and human factors people tend to live. These two schools of people tend to be raised in different academic traditions, they use different tools, and they speak a different language. Often you'll find they don't even work in the same building. And so the question is, where is interdependence in this system? The answer is right in the middle. This is where the requirements for supporting interdependence come from. And that's the area that you need to design for. It requires both the knowledge of the right-hand side, autonomy and control theory, and the left-hand side, interface design and human factors. Three key things you need to support interdependence are observability, predictability, and directability. So why these three things? To answer that, you need to ask yourself, what are the core issues in human-machine teaming? For anyone who's worked with a system before, of any kind, you've probably asked yourself this. What is it doing? What's it going to do next? How can I get it to do what I need it to do? These questions are not questions about automation or function. These questions are about interdependence, and specifically support for that through observability, predictability, and directability. There are corollaries on the machine side, as the machine will need to know the intent of the human sometimes. It would also need to know, what does the human need from me? And it might need to know if the human could provide help or not. And so these might be mutual constraints. Observability refers to how clearly pertinent aspects of one's status, as well as one's own knowledge of the team, the task, and the environment, are observable to others. This is commonly referred to as transparency, but we prefer observability. Transparency implies that you get all of the information, but good communication is efficient and you only share what's necessary, thus observable. The complement to making one's own status observable to others is being able to observe their status. Predictability refers to how clearly one's intentions can be discerned by others and used to predict future actions or states. The complement to sharing one's own intentions with others is being able to predict the actions of others. It involves the capability to receive and understand information about the intentions of others and to be able to predict future states and take those future states into account when making decisions. Directability refers to one's ability to be directed and influenced by others. The complement is to be able to direct or influence the behavior of others. So Coactive Design highlights three key capabilities needed to support interdependence: observability, predictability, and directability. Sometimes I abbreviate those as OPD. So let's go over a few examples of how you might identify observability, predictability, and directability constraints in a given system, and then compare that against a function-based approach. Consider that you have a bunch of old records and you'd like to play them on your computer. You'll need a music player, and so how would you design this technology? A function-based approach would know that you need to save those records onto your computer, load a particular song, start playing that song, and eventually stop that song. Those functions are common for any music player. An interdependence-based approach would start differently. It would ask how you interact with that system and find the interdependencies in that interaction. For example, you want some things to be observable, in particular when you're working with selection. You would want to be able to observe what music is available so you know which one to select. You also might want to know information about the current selection playing. To support predictability, you'd want a system that allows you to determine the upcoming sequence of songs. You might want to play your favorite songs from a particular album. Or you might want to randomly go through all your music as a shuffle. You might want to be able to predict what the next song is going to be so you know if you can skip it or not. And to support directability, you might want to be able to pause a song if you get an incoming call and then resume it. Or you might want to skip a song if you don't like it, or just ignore a song from your playlist in general if you're tired of it. These are all examples of how you might support managing interdependence within your system. Any system will support the function-based requirements. The best and most popular ones tend to support the richest interdependence requirements. As another example, consider the unmanned drone. The functions are pretty straightforward. You'll need to be able to take off, hold altitude, fly some waypoints, orbit a destination, return home, and land. Those are just a couple examples. From an interdependence-based approach, you need to consider what you need to be observable. You might want to know what the current altitude is, which waypoint is next, or how much time until you need to return. From predictability, you might want to know what are the waypoints that are planned, and also what current emergency divert plan do you have. And from a directability standpoint, you might want to be able to specify a new altitude, or alter some of the waypoints but not all of them, or maybe just adjust your orbit by either changing the destination or the direction of orbit or the range of the orbit. These are just some examples of how interdependence might drive that design, but a lot of those would involve changing the underlying algorithms to support that need, and that is why interdependence-based design is so important. One last example of a medical assistant. Some of the functions a medical assistant might provide is to scan a patient, measure some vitals, conduct some analysis, generate a diagnosis, and make a recommendation. From an interdependence standpoint, we might want to be able to know what vitals were good and bad. I just don't want the recommendation, but I want to know something about the underlying features, more detail. I might also be curious about what was included in the assessment and what was not, because that might help me determine whether I take that recommendation. With respect to predictability, I might want it to alert me if there's any issues that were identified that I didn't come in for. I also might want to know that it will direct me to a specialist if it's uncertain about its answer. And from a directability standpoint, I might want to measure something additional, or include additional considerations in the analysis that were not part of the original function. This example is a bit more sophisticated than the other two, and it involves almost a negotiation that is commonly found in teamwork. This type of mutual adaptation is critical to effective teamwork and only comes through designing for interdependence. So hopefully I've shaken up your views on autonomy and AI a little bit and gotten you to think a little bit differently. I wanted to convince you that adding automation or autonomy or AI is not about replacement. Automation is not just about allocation, but also integration, and the overall goal should be building a system that can work interdependently. I also presented coactive design, an approach to understanding teaming based on interdependence. In doing so, I proposed that interdependence should shape autonomy. I also highlighted that observability, predictability, and directability are the foundational capabilities needed to support interdependence. Coactive design is important because there are design implications involved in supporting interdependence, and also because the best systems support rich interdependencies. So in conclusion, although counterintuitive, the greater the individual competence, the greater the need for sophisticated collaborative skills. A lot of people find that strangely counterintuitive, but you'll find it common in almost every application. The last three examples were examples of that. I'll give you two more. Just consider the person who checks you into the hospital compared to the person managing the surgical team. Who has the greater individual competence, and who has a need for more sophisticated collaborative skills? As a second example, consider a security guard versus a SEAL team member. Who has the greater individual competence, and who has the greater need for sophisticated collaborative skills? The answer should be fairly obvious, and it points to the fact that as we try to build more intelligent and capable and sophisticated technology, those capabilities will need to be matched by equivalent sophisticated collaborative skills. That's the last point of this talk. Hopefully you're beginning to understand that as you increase the competence of your technology, you'll need a matching increase in collaborative skill. And I also hope that you understand that designing for interdependence is a key part of that challenge. If you'd like to read more, you can go check out some references found on my website. The last thing I'll leave you with is a quote from Yogi Berra. In theory, there's no difference between theory and practice. In practice, there is. I've talked a lot about theory, but I also have some tools to help you along the way, and that's for next time. Thank you for joining me in our discussion about No AI is an Island.